All right, this is the second lesson out of chapter 13, and it deals with um, energy requirements for changes of state. Now, there's actually a number of changes of state. We can just review those real quick. You can go from solid to liquid, that's called melting. From liquid to solid, that's called freezing. From liquid to gas, we call that boiling. From gas to liquid, we call that condensation. And then it's actually possible to go straight from gas to solid, or from solid to gas, which is called sublimation, and from gas straight to solid, which is called deposition. But we will be primarily working with the two phase changes that you're aware of. That would be melting and boiling. And that's when we're adding heat. If we're going the opposite direction, it would be condensing and freezing. It requires energy to change something from a more condensed or a more lower energy state to a higher energy state. So when we take something that is a solid, if you watched that video that I asked you to watch, the molecules are actually linked together. They're held together. They are held together by a force called an intermolecular force. If I have two molecules here, and these two were in a solid state, this molecule, you have to pretend that right between this blue and this pink ball, that there's actually an attachment between them, a force that's holding them together. And because this is in a whole bunch of molecules, these are able to vibrate back and forth, but they're not able to move. If we're going to change this into a liquid, we have to snap that bond. And that bond then becomes free. Now, in a liquid, these are now free to move around, but as we said before, they really aren't free to just go anywhere they want to. If these two are near each other, they may bump into each other, push apart, but immediately there's another molecule on this side that's pushing it back. And it's like molecules are in a crowd and unable to really go anywhere. If you've ever been in a large crowd of people and you're trying to move, even with purpose, trying to get from one place to another, it's hard to do because you keep bumping into people. Finally, what's holding the water together, even though these are free to move around a little bit, what's holding the water together is also an intermolecular force. And to break that and allow these two now to separate and go as far apart as they would in a gas requires more energy. The energy that we will be using, before I do that, let me just mention, by the way, that all takes place because there are positive and negative ends to the molecule. And positive and negative ends are like magnets, north and south ends of a magnet. Opposites attract. A partially positive end will be attached to a partially negative end. In your book, they're going to talk about intermolecular forces and intramolecular forces. In English, this word inter means between. And this one means inside. It's not exactly the best way to put it, but on here, if I have these two, and remember this is partially positive, partially negative, there is a force that is between these two molecules. Since it's between the molecules, that is the intermolecular force. This that is holding these two together is an intramolecular force. This is inside of the molecule. These are between the molecules. An example for that would be we have CIF, which is California Interscholastic Federation. It's where you have competitions between schools. So we've got Fresno Christian, and we have say CVC or Emmanuel or one of the other schools that we might play. And those two schools are separate schools, but there's a competition between the schools. But if we had a sport that we wanted to play, like the powder puff football, we put teams in our own school. That's an intra. They used to call them intramurals. They were when schools didn't have a big enough league, or they didn't have somebody else who wanted to play. Schools sometimes in the old days, especially if you were somewhat isolated, would put together teams within the schools and you would play against each other. That would be intramurals, whereas these would be intermural, where we're playing other schools. That's the idea. So you're going to see this a lot. When we start working with energy changes of state, this intermolecular forces is what determines the energy needed. To change states. The intramolecular forces would be what it would take to break the bond of the molecules. Now, when we talk about the energy needed, you need to know that energy and heat are, for us, going to be essentially the same thing. The symbol is Q for both of them, and the unit is the joule. J stands for joule, and that's Joule, not Jewel. It's named after James Prescott Joule, who did a lot of work on steam engines and whatnot, and was one of the ones who figured out that energy and heat were the same thing. Heat measures motion of the molecules. It's actually the total amount of motion of molecules. If you increase the heat, the molecules are moving faster. And then we're going to get used to this term, heat of fusion, and that has a symbol HF, and heat of vaporization, and that has a symbol HV. The heat of fusion is the heat required to totally melt a certain sample of material, whatever substance we would have. And heat of vaporization is total heat needed to totally vaporize it. Do you remember this graph from last one? We have ice, and then it goes up like this. During this period of time, a certain amount of heat goes in because we were going this direction. And from here to here, a certain amount of heat goes in. This right here would be the heat of the heat needed to melt it. And this would be the heat to boil it. Now, the heat of fusion and the heat of vaporization are actually numbers for every material. So I have three of them up here. For lead, it takes 23 joules for every gram to melt lead. So if I have 100 grams, it's going to take 2,300 joules to do that. And 860 joules is my heat of vaporization. Zinc is 112 and 1760. Water is 334 and 2260. Now, you're not going to be expected to know where these numbers come from. We get them from a table. But I do want you to look at something kind of interesting. And that is that the heat of vaporization is much greater than the heat of fusion. Heat of fusion is 23 and then 860. This is about 40 times larger. This is about 15 times larger. This is 7 or 8 times larger. It takes more energy always, or I shouldn't say that, there's probably some exception. As far as I know, it always takes a lot more heat to vaporize something. And that's why we would say that the two condensed states of matter are actually more similar than the expanded or the gaseous state of matter. Another interesting thing, look at the heat of vapor or heat of fusion of of water, and even the heat of vaporization of water. Heat of fusion of water, to melt water requires more energy than to melt the same amount of lead or the same amount of zinc, and that's actually somewhat surprising for most people. Now, with all of that, it turns out that the lesson today is actually fairly easy. There is an equation. Q is equal to mass times the heat of fusion, or Q is equal to mass times the heat of vaporization. And you're going to be asked how much heat that it takes to change state. This is the heat, this equation could be written this way: mass times heat of fusion / or comma vaporization. This is the heat needed, the energy needed to change state. So let's just do two quick problems. Actually, we'll do a couple. Let's say we ask this question: how much energy is needed to completely melt 150 grams of lead? Okay, so there's some decoding in here. It's melting, so we're going to use the heat of fusion. We have our mass, and all you need to do is go Q is equal to mass times heat of fusion. Q then is 150 grams times 23 joules per gram from right there. And now we would simply multiply those together. 150 times 23 is 3450. But because of two significant digits, we could round that off to 3,500 joules, 3,500 joules. All right. Let me do a different one. How much heat is needed to completely vaporize 3 moles of zinc? Okay, so once again, we're looking for the heat. We're talking about vaporizing, so this is boiling away, and it's not in grams, it's in moles. So this problem has a little twist to it. Our basic equation is mass times heat of vaporization, but I don't know what my mass is. So before we do anything else, we have to take 3 moles of zinc, and we need to change it to grams. 1 mole of zinc is 65.5 grams of zinc, and that's going to be 195.5, I think. 65.5 times 3, 196.5. We'll just round it off to 197. And so this will be 197 grams times the heat of vaporization, 1760 joules per gram. Notice the grams will cancel. 197 times 1760, and this ends up being 346720. We'll round that off to 347,000 joules. Notice how much more it is than this one over here. All right, and then one last one. Let's say that we have how much heat is needed to vaporize, let's do melt, to melt a 1 kilogram block of ice. All right, 1 kilogram, there's 1,000 grams per kilogram, and this then would be 1,000 grams. So it's going to be this equation, mass times heat of fusion, and it will be 1,000 grams times 334 joules per gram, and 334,000 joules. So there is a worksheet that we will be asked to do. I'm not going to have you do problems out of the book, but it'll be a worksheet that's called change of state. And if you could just write down the answers, but you need to show me your work because I have the answer below. So just sending in your answers isn't going to be good enough. You need to actually snap a picture of it and send it in and show me the work that you've done. It's real easy work, but again, this will be called a change of state handout. It'll be linked. So, and real simple. And then next lesson, third lesson, will be very, very similar, but it has to do with changing the temperature, where change of state is a little piece of that. So, all right, with that we will end, and we'll see you on the next video.